Okay. Hello, everyone. Welcome. Thanks for coming. Let's start episode 9 of Warsaw Quantum Computing Group. But it's the first meeting in the new academic year. And today we have a special guest, Jacob Biamonte from Skolkovo Institute of Science and Technology. And he will give a lecture about variational quantum machine learning. Before he starts, I will also give you a short intro and say a few words about Warsaw Quantum Computing Group. So first of all, this meeting is supported by Daftcode, which is our strategic partner and sponsor, and Google, which is our host today. So we are very happy that they support us. Probably some of you remember that several months ago, in 2018, we started this group. The first meeting was in November 2018, titled Introduction to Quantum Computing. And yeah, since that time, our group has grown. Right now on our Facebook group, we have more than 500 members. And we organized 8 meetups. So the previous meeting was in July, also here in Google Warsaw office. So you can see the titles of our previous meetings. And if you are interested, feel free to join our mailing list, our Facebook group, and follow our YouTube channel and fan page or Facebook. I will also say a few words at the end. Also, I will give you a few announcements. Right now, the important thing is that we expect that the lecture will last about 1 hour, maybe a bit less, and there will be also time for questions and answers. And finally, there will be the after party, the networking part. So we ordered pizza. It will arrive about 7:15. So we hope that you will also stay with us, and there will be opportunity to network, meet other people, ask questions to Jacob, who will also stay with us for some time. All right. Okay, so Jacob, I think we can start. Yeah, please welcome.
Thank you for the introduction, and thank you all for coming to this lecture. So I'm going to tell you an ongoing story. It's a story that is causing the world to speculate. It's a story that's causing me to think as deep as I can. And it's a story with more questions than answers. And I would call my group kind of the adversarial group, right? We are removed from industry at some level, and we're trying to break this stuff. And the act of breaking it is allowing us to really see, I think, into these algorithms a little bit more. And so let me go into it without further ado. So this isn't working in the way that I like it to work. Perhaps I should.
I think you can just.
Oh, wrong arrows. I'm better with quantum computers. So before we get started, like any, mid to senior career academic, what they'll normally do is cite themselves like crazy. So there's mine. No, but really, these are relevant to the discussion today. And so Pavel told me that there was a number of, let's say, younger scientists that are about ready to make the worst mistake of their lives by going into this field. And so here's a good way to get yourself started. The tools that we're using now, the tools that we're using today, this was really a theoretical discipline not that long ago. And especially, let's say most of the mathematical physics was on the channel side. Okay, there was kind of a smaller community of us on the computational side that was doing, let's say, more of the mathematical stuff. So now you can get some of those techniques out of a few of these papers, especially the tensor network stuff. The tensor network methods is going to be very useful. And what are we talking about? So why is the whole world on fire with this, okay? The time scales of a physical process can be much shorter than the time to simulate that same process with a computer. So the innocuous idea that instead of simulating a system using, let's say, Python, okay, or PyQuil, which I think Pavel uses, okay, instead of using that, I just let the system do something. Now, this is not some proven fact, but this is a conjecture. but it's a conjecture that there's a lot of evidence to support. So even today, let's say the University of Warsaw, I'm just guessing here, if you go to the mathematics department or the theoretical physics department, there's going to be a fluid dynamics group. And to this day, you can take a very simple configuration and you can actually do something physically that you can't predict very easily, and sometimes not at all, using the best computational methods in those groups. Okay. And that's very profound. And I was giving a talk actually last time, and I said, oh, I have a bucket of water and it's freezing outside, and I throw it and I can't predict the formation of that matter because of quantum effects, therefore quantum supremacy. But something's missing, right? And I have a very brilliant provost, unfortunately. And so he brings me to his office. I'm like, okay, what did I do this time? He builds batteries. Okay, he's a theoretician for batteries. And he says, tell me about this quantum computing, okay? What are you going to do with it? What's the best application? And so we talk about, electronic structure problems, machine learning. And he sees me again and he asks me a couple questions. Then he comes to me and says, here's my paper. Here's the numerical plot. Here's where numerics don't work anymore. And here's where our experimental data fits. So this is quantum supremacy in his mind. And he's somehow sort of right. Or is he? It's interesting. What is quantum supremacy? Okay, so we have the game, the adversarial game that Google just played, but the concept is very, very simple. You build something that you can't predict, but you want it to have some degree of programmability, okay? And we're leveraging on this original idea of, Richard Feynman saying physics, quantum physics is particularly hard to simulate. Therefore, it must be particularly powerful as a computation. Now, the idea is to build the physical system and then to measure it. But the question that you must ask, and this is the important part that separates that bucket of ice or my friend's batteries, how much can you do with a little bit of programming and a little bit of control? So I want to make this quantum system reconfigurable, and I want to make it have as low of errors as possible. At what point does this thing become universal? We don't know, but I'll give you some partial answers to that today. At what point does it become capable of simulating a real-world system? Now, there's an old story. It's called error correction. You got crazy people on the left saying, oh, it's going to violate thermodynamics, second law. Okay. You got other crazy people on the right saying that if you don't have this, then you can't do anything. The truth is, it's a sufficient condition that guarantees if you do have it, you can do quantum computation. Anything you want. That's a sufficient condition. It doesn't say that without it, you can't do it. You can't do anything. So I believe you need it, but do you need it? So let me ask you another question. Right? I'm not one of those crazy people that believe you don't need error correction. So if you absolutely believe you must have it, you might be just as crazy as if you absolutely believe you don't need it. So here's the question. Are there quantum systems that exist in the world today, real physical systems, that you can't simulate? Well, there's even classical systems with the wind tunnel experiments that you can build that you really can't simulate. So the answer is yes. And those systems do not have error correction. So it gives us some hope that if we can program one of these devices and control one of these devices, maybe there's something beautiful there yet to be discovered. And maybe the simplest idea is this, okay? So if you're going to talk to a sponsor, you say, well, there's no reason it's going to go slower than classical computation, right? But say, well, actually there might be, okay? Because the timescales of, let's say, a superconducting transistor are very tight. That transition is very tight. Okay. So if you're going to talk to a scientist, you say, well, what happens if I increase the amount of quantum effects in, let's say, the D-Wave system, the D-Wave quantum computer? Will it become better, right? So those are the types of questions that I would say got the field sort of started. And where are we today, right? So many of the early ideas, most of the early ideas. So when I started this field, I was like, okay, this is going to be great. We're going to build one of these things, and I'm going to go over here and do this calculation, and somehow that'll be important for that. And we had 2 qubits for the longest time, didn't we? Really 1 qubit. And suddenly now we have more. Okay, we have many more, right? And we have sort of 2 different classes of devices. Okay, we have these ground state quantum computers, if you can call it that. I like to call it a quantum annealer. Okay, this is the D-wave machine. Then you have the time-dependent, time-controlled, pulsed system. It's no more of a quantum computer than the D-wave machine, guys, by the way. Both of these things lack fundamental things to make them what would be called a quantum computer. So the quantum computer is this enigma that we can't build. And the thing that we can build now is what everybody's excited about. So originally, to get the money to build it, is anyone an experimentalist here besides Thomas? So the experimentalist who, these people have single-handedly destroyed theoretical physics. They pushed all of the theoreticians into math and computer science departments because unless you're doing something directly related to their experiment, they don't like you. Okay, but in reality, okay, these people told everybody, oh, the only thing you need is to build a quantum computer. Give me $1 billion. Then the second they got the money, they're like, by the way, we don't really know what works with the applications, but we discovered this new thing called a variational algorithm, and it's going to be great. So, and you couldn't make it up, and that's happening now. Here we are today. So that's the history of quantum computation in a nutshell. And where are we today? So how many people have actually studied variational quantum computation? Okay, so there's one person, a few people. There's a few people here, right? So if you pick up a book on quantum computation, you pick up Nielsen and Chong, beautiful book. You can learn the notation, which I actually think is bad notation, but that's another point. So you should do everything with tensors, but you can learn the notation. You can light it on fire and throw it in the trash, okay? Because none of that stuff works, okay? There's actually not a very good book on modern quantum programming. The field hit the reset button. It totally hit the reset button. I'm going to show you a talk today. I'm going to prove that this new thing that we have is actually a universal model of quantum computation in principle, okay? It's unlike the other models. And all of the optimism of what, for example, Google, we're at Google, okay? If I say anything too bad, there's going to be a lightning beam that comes down on me. Okay, they're going to pull me off the stage, so I can't say anything too bad. So, okay, guys, Google's a little bit optimistic about their variational algorithms. So today we're going to break it. So what they've done is all of this hype, the speculation, what they've done is they've picked statistically insignificant, non-representative examples. We'll show that later. And the performance of this QAOA thing is based on that. We'll show that later. Now, my talk is just as pessimistic as it is optimistic. I go through and I break a few things, and then I tell you, well, I'm not sure how bad we broke it. Then I say, by the way, you can do machine learning with all this stuff. Then I mention, we're not really sure how well that works, actually. Then I tell you it's universal. So what am I actually saying? I don't know. It's Ouroboros in a talk, but it'll be very entertaining, I hope. So behind every great talk are great students that were greatly tortured. Let's not forget those students. And these are great students. And Igor is not a student, obviously. So Igor, we had to pull in kind of a big fish program. He writes parallel code. It's some crazy stuff. And the moment when I knew that my students might end up hating me is when poor Akshay, he's like, yeah, I learned how to write a for loop a week ago, and now I'm doing parallel code. He's just spent all winter trying to produce this data. And because the data wasn't what I expected, what I do is I do blind reproduction. So I separate them and have 2 teams doing the same thing, and then we make the same plots, right? This is science, okay? That's the way it is. So your first year, you do a theory PhD, you got to write a piece of code. That's it. No exception. So that's what these guys did. And we discovered some stuff along the way that's quite fun. So the first part, no quantum. So all of the statistical physicists in the audience, which is probably none, there's nothing about this that's quantum. 0 quantum. The first thing I'm going to do is I'm going to show you guys how to benchmark, okay, from a physics perspective. So how do you benchmark from a physics perspective? Well, you go back in time to the 1990s when physicists got interested in satisfiability. And when they got interested, they came up with something called a computational phase transition. And anytime you say the word phase transition, you make 3 people angry and they're all angry for different reasons. Okay, so I say phase transition signature, right? And it's a computational phase transition signature. So if you read the words very carefully, everything's fine. So don't get angry. Now, the K-satisfiability problem is very simple. All it is a Boolean formula. You're trying to find a solution to this formula. Or if you're trying to minimize the number of conflicts in this equation. Okay, so imagine some equation takes binary input, spits out, let's say, a real number. You want to minimize that real number. When you minimize that real number to 0, you say the equation is satisfiable. Now, the K-satisfiability has a specific form. Okay, you put together products with K variables in each one of those, and you can generate these things randomly. Okay, very simplistic technique, standard random number generator, nothing fancy. Okay, and we let a K-sat instance will consist of m clauses over n Boolean variables. So clauses, that's the number of terms in your formula. Okay, the computer scientists are like, this isn't very exciting, man. The physicists are like, what is he talking about? Now it's going to be fun for the physicists because we have something called the clause density. Physicists love densities. That's the number of clauses divided by the number of variables. Here's the magical part. This is a tough plot. This is a beautiful plot. So don't ever think that something is too simple to inspire a lot of people. So we didn't come up with this first, but the blue thing, we generate thousands of random satisfiability formulas. They go from being satisfiable to not satisfiable abruptly. Okay? You can explain that with statistics. That part you can explain. By the way, it's easy. It was easier to explain on the left. That is for 2SAT on the left, which is, that's in P. There's an algorithm that'll solve that in P. It's a language decision problem. So actually the way that computer scientists state things, they just want to basically separate the yes instances from the no instances, and they call it language recognition. The way that physicists think of things is they try to optimize, they try to minimize, right? Which is called actually max sat, okay? And we'll go into that in just a bit of a second, but the point is the blue curve, the 100 means 100%. Okay, if I give you one clause, is it satisfiable? Yes. It's always satisfiable, one clause. What about two? Probably, depends on how many variables. Eventually, you get to a point where it's not satisfiable anymore. The red is the runtime of the algorithm to make that decision. The algorithm has to tell you, is it satisfiable or is it not satisfiable? Why does it jump up at that phase transition? So this is the fakest real thing you'll see all day. The blue curves, based on some sophisticated mathematics, we can predict the shape of them. Okay, by the way, it was a tricky thing. The exact point of where that is, it changes in the infinite limit. Okay, everything you're looking at now is finite size effects. Okay, but why is the algorithm blowing up at that point? And what does the blow up look like? How, is it exponentially sharp? What does it do? We don't know the answer to that. Okay, but we believe that the hard instances are concentrated around the phase transition point. So in other words, there's a little window, and if you generate instances inside that window, those are tough. And if you generate them outside of that window, those are easy. Okay, so in other words, if you give me an instance way over here, I can just guess and say, hey, you know what, it's probably not satisfiable, right? Just because of that ratio. Okay, so good. So here's the question. First question of the day. Can you build a physical system to see this effect? And to answer that question, which I had that question for a while, there was a team, NTT. They built this optical parametric oscillators, right? Somebody's heard of that before? Somebody's heard of it. Nobody's heard of it yet. So somebody heard of it. Okay, so what this is, it's a simulation of an Ising model. Okay, and they use these to solve constraint problems. So what we wanted to do is we wanted to say, okay, look, this thing basically produces an output state, which is some type of distribution. We don't know if it's a Gibbs state. This is another debate in physics. So things don't really reside in Gibbs states except for in special cases, but it's an approximation to what it actually is, and that's fine. So there's some distribution. Can you see this effect in the distribution? And so here's what we did. we take the Gibbs state across the phase transition, and we look at the probability of measuring the system in its ground state. Okay, we're going to replot this in terms of energy in the next round of this because it's a little bit easier to understand. And I'll go to the next thing. What we found is the following. So remember, there's finite size effects. That black line replaces the blue line in the previous thing. Those are just your instances going from satisfiable to not. And interestingly enough, you see some kind of dip there, which in other words, the physics of these Gibbs states is showing that this thing has low overlap with its actual ground state at the phase transition. And there's things we don't understand about this plot. So there's some finite size effects. So we wouldn't expect it to go back up again, maybe. So we don't really understand why it's going back up. We're sure it is doing that. We think it's a finite size effect. We don't have a good theory for that. So people, I don't think this is the right workshop for this, but when I was in Stockholm, there's a number of people, they do statistical physics, and they went crazy. They were so excited about this, right? Because they haven't had an open question for 100 years, basically. So I was like, hey, this is an open question. We probably will not be able to answer that in my group. Anyway, but the point is this. Something magical. Nature's like, F you, man. You can't solve these things, right? You can't solve these things. Okay, so there's some interesting connection between computational complexity and physics, okay, based on this one example. So we generalize to all examples based on this one. Now the question is, what does quantum mechanics do to this? So the original concept of this project was, okay, first, I didn't like the way anybody was benchmarking. I was like, this is nonsense. They're just randomly making stuff up, and there's no like systematic thing. They don't know where the hard thing. I got sick of going to these workshops because I never really went to these workshops before. I go to these workshops, like, wait a minute, you guys have been doing this for like 15 years and you still don't know how to benchmark? You still don't know where the hard instances are? Every time one guy would come out with a hard instance, someone else would say, no, that's wrong. Okay, so here's where the hard instances are. At least this is from classical computational theory. What does quantum mechanics do now? Does it change the shape of that algorithmic runtime? So that was the original question. Unfortunately, and this is just showing that, going back, so this is just showing that there is a maximum. So at some finite temperature, there's always going to be problem instances that you'll have low overlap to the ground state of. And this is showing that you need to basically lower your temperature and it will max out basically at the phase transition point to get a high overlap with the ground state. So in other words, this is replicating that there is a maximum there, which I still find surprising. Now, the next point is, okay, and we're going to kind of build up to this. So what is this variational quantum computation? So we're kind of putting this, we're putting this idea about the phase transition kind of aside for now. But the point is that physical systems perform differently on different problem instances, which you would imagine that this is true. Algorithmically, we know it's true. We know that sometimes you give me an easy instance, I can solve it very fast with some Python code, right? But physical systems, they're kind of agnostic to what you feed it, or are they? I mean, the runtime of these machines is always the same, guys. That's one of the reasons why the benchmarking problem was so hard for so long. It's always the same. Just run it, run it, run it. So where are the hard instances, right? At the phase transition signature. That's where they are. Now, we're going to try to apply this technique to quantum mechanics. We're going to see, does the quantum computer do anything different? Let us find out. Firstly, we have to tell you what a variational quantum algorithm is. And it's the simplest thing you've ever heard. It's very simple. All it is a circuit or a sequence of operations that I can adjust the parameters of. So I have a parameterized circuit and I can tune it. And I can run it many, many different times. So for example, I could calculate the expected value of energy for that state, given some Hamiltonian that I can measure, which is what that is in the second part. That's it. These are just some sequence of unitaries. They all have angles, and I adjust them. Okay, so Google's quantum supremacy that they just did, they take what's called the hardware efficient ansats, and they randomly make some assignments, and then they basically measure this thing a lot of times, and they spit out some curve, and then they say, okay, can you reproduce this curve classically? Right, so it's very similar to that model. This is where this is coming from. The next piece is you have the variational state space, which is the space of possible assignments that you can make in your circuit. That forms a vector space, which is a subspace of your entire space. In principle, it's a subspace because your circuit's going to be very short, so you don't know, you don't expect it to span the entire Hilbert space. This is your computational resource. Given measurements in the sigma basis. That's it. This is the model now. So I can prepare a state and I can measure polystrings. That's it. That's the model. And I can iterate this. So every time when I prepare this state, and I might have to prepare it multiple times. So to get epsilon error, I have to do 1 over epsilon squared measurements. So it's not the best model in the world, but we hope that it can still do something. So I make those measurements, I adjust in a feedback loop, and I change my parameters. And this is a technique basically very close to machine learning. Okay, it's just some optimization loop. This is variational quantum computation, and I'll argue later that this is actually universal. Now, for those of you that have worked on quantum control, okay, now this is the reason why I think it's a little bit beautiful, and we'll talk more about that later. So first of all, who knows what quantum control is? Yeah, so you guys know what quantum control is, right? Quantum control is awesome, but quantum control doesn't work because quantum control, you have to simulate your entire system. Okay, so I'm going to show you guys a way that, that I discovered that removes that. Okay, so, I think it's important. So you start off with a gate sequence. You could feed that into, let's say, grape. Grape will spit through and create the same effect as that gate sequence using what is called a control sequence. Okay, but in order to do that, you have to simulate the entire system. But here we create what's called a bounded objective function. A bounded objective function makes the quantum computer do all the work, then I measure and I have a function that I'm trying to minimize. Okay, so if you have some kind of circuit that allows you to basically do gradient descent on this function, which is possible, by the way, we have another project on that, then you can basically replace a lot of this optimal control stuff. And the idea would be, instead of having a sequence of gates, you start to compress this as much as possible. Okay, and we're hopeful that if you can compress it enough, you'll be able to basically run an optimization loop that you can use these near-term noisy quantum computers to do something more than quantum supremacy. And so people, right now, everybody's like, hey man, you're actually saying this stuff is universal? It's like, no, I don't think it can do everything, right? But I think that this model of variational universal quantum computation can probably do some stuff that will be, let's say, outside of just chemistry simulation. That's what I'm arguing. I don't know what the answer is. The next thing we're going to try is obviously factoring. So again, we'll say that the objective function will accept if you can get it to go below some value delta. Okay, so it's very simple. I'll just explain it again. So we're not trying to, it's like some guy with some weird notation. Who's this guy? Whatever this is. Okay, garbage, whatever. Let's forget about it. Let's just explain it one more time. I can prepare a state as many times as I want, provided the number of times is a polynomial in the size of the system. But let's just ignore that. So I can prepare the state multiple times. Then I can measure each state in different bases. Then I can take all that information, put it up in some convolutional step, and spit out a real number. Then I give all the settings to some complex algorithm, which is a classical algorithm, and it says, okay, now change your parameters on your state and do it again. So it's a feedback loop. And this feedback loop tries to minimize this function. And of course, function minimization is very easily seen to be quite computationally challenging. Okay, nonetheless, it can be done. okay, for 50, even 100 variables, right? And the question is, can you do this and use this to make the quantum state of the system do something that classical computers can't do that is also useful from some technological perspective? Now, remember, in this model, the state is never stored on the classical computer. And it is assumed that that quantum state, to store it, takes exponential memory, right? And that is also the assumption behind quantum supremacy. Now, what are the functions? What are the objective functions? So just ignore this equation because it's written in a funny way. So what are the functions? Well, an easy function could be, let's say, an electronic structure Hamiltonian. I have a Hamiltonian, and I say, okay, we know that the ground state, we know that we want to find the ground state energy. We don't know it. So we try to run this thing, and we don't know if we're ever in the ground state. We don't even know if we're in an eigenstate. How do you know? So that's one of the interesting questions. How do you verify these things? Well, you can verify it. So you can verify it by looking at the divergence, which is also, if you can measure h in polynomial time, you can measure the divergence in polynomial time, so that if that goes to 0 or close to 0, then it'll be in an eigenstate. So that's good. So I can actually reference this, and then I can check the energy. Now, with chemistry or with some physical system, I don't construct the Hamiltonian. So in the early days of quantum computation, Alexei Kitev and some other people, Turhal, Aronoff, et cetera, I don't know if anybody was there at that time, and also I wrote a paper on this, okay? It's about the complexity of local Hamiltonian. And the concept was simple. Kitev said, so K local Hamiltonian is a K-body operation. That's easy to show that that's difficult to find the ground state of, because you can easily put a circuit into that and do some other stuff. But what he said is finding if the energy is below a certain value or all the energy is above another is the quantum analog of NP complete, QMA complete. And what he did is he said that 5-body Hamiltonian was QMA complete. Then people went to 3, then they went to 2, then I went to basically ZZ plus XX or ZZ and XX. And then other people have kind of like narrowed this down. And here in this model, it actually doesn't matter if it's 5-body or 10-body or 20-body because you're just making these simple measurements. So that's one big advantage of this model, okay? The disadvantages, of course, is you have to measure this multiple times, right? Now, the first thing that you'll do with this model is we're going to go back to the original thing that we talked about in the first part of the talk. We have these SAT instances. We can put those into a Hamiltonian form. We could try to minimize these using a variational circuit. This is called QAOA. QAOA is an assignment of those parameters in that circuit to try to minimize a satisfiability instance. That's it. Now, we'll get to the part where we break Google stuff. So here's how it works. And this is a very nice idea by, Eddie Farhi and some other people in the paper. And the point is this, you have your ansats now looks like these intertwined operators, and you're allowed to adjust these independently. And if you remember from your adiabatic quantum computation lecture, which happened because I saw the slides, they extrapolate between an initial Hamiltonian, which will be in the X basis, and a final Hamiltonian in the Z basis. If you extrapolate slowly enough over infinite time, you will maintain in the ground state the entire time, provided this is a gap system, and you can actually turn that into a real theorem. The initial adiabatic theorem was not actually a theorem. It was just something. So staying in the ground state. So you can turn it into a theorem, and you can simulate an adiabatic process with a sequence of gates. And you could do that, which is called the Trotter sequence, right? These are integrators, right? So we're using all the different words for the same thing. This is not that. This is just a sequence of gates that you randomly assign parameters, and you hope that it works. You hope you get the same output, okay? And it turns out to work very well as long as you're picking from a very small statistical subset of your problems. And again, in QAOA, you're trying to minimize this real value that you're getting as an output. And the output that you're getting is the number of clauses that you violate. okay, in your SAT instance. And by the way, there shouldn't be a line right there. That's from my graduate student. And I flipped out on his first year PhD evaluation for it. And I asked him to put his slide in, and I'm going to flip out on him again. So I was like, hey, can you put that slide in? Anyway, so just pretend just erase this. So what happened was, just imagine you're a PhD student and your supervisor takes your paper. And I was like, no, not less than or equal, it's definitely less than. So I put a line through it. I put a line through it on the paper, and the guy puts a freaking line through it because he trusts me. And he's like, you told me to do it. And he's like, I didn't understand it. You told me to do it. I'm like, no, I want it gone. He's like, well, why do you put an X then? Why'd you only put one line? So anyway, so maybe, okay, so here's the thing. This is the real minimum energy of your operator. This is your Hamiltonian. This is the true minimum. This is the approximation, which is obviously a subspace of H, right? That's the circuit ansatz, okay? This difference is greater than or equal to 0, of course, because of the variational principle, right? Basic quantum mechanics. But there's more. Turns out that the sequence of gates cannot get to the ground state of these Hamiltonians, but it's worse than that. It's worse. So this is what we call a reachability deficit. This thing is equal to a non-vanishing function. We know it's non-vanishing because we have numerics. Okay, we bound it in certain cases. We can look at if the function behaved this way or that way, it would change something in the polynomial hierarchy, blah, 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 blah. But in reality, here's what you got. Linear dependence of crappiness on clause density. So in other words, clause density goes up for a fixed length circuit, your approximation goes down. Google's results, they're reporting, this is clause density 1. That means that your graph perfectly overlays on your couplers, okay? In a very small, finite, tunable range of parameters. That's where all the stuff is in the literature, guys. So everybody's like, wow, it works so great. No, it doesn't work that well. You just have to turn up, you have to make the problem density go up. Then it works not well. Okay, so this is, I think, an important finding. We didn't have any idea of how to break this stuff when we started. I initially wanted to see these phase transitions. We didn't see a phase transition for various reasons. We know why. What we're seeing is we're seeing something different. The algorithm will not get to the solution. That's what we're seeing. And its inability to do that grows with the clause density. Now that the poor student, these guys are very good, by the way. I mean, this guy got, he won the Raman Award in India for his master's degree. So we decided to hire him. Okay, so this guy, you'll meet this guy eventually. So first he discovers this thing, and then he's like, well, what do I do now? He's like, well, now you have 3 or 4 more years to do the theory of this. And he tells me, he says, but this is so simple, we shouldn't send it to PRL. I was like, look, I've never sent anything to PRL before in my life. It's simple enough, it might get in. And so, we don't know what's going to happen, but he got, so this is another story. But the result is very convincing to show that this stuff has a serious limitation, right? How can we overcome that limitation? First, we have to find it, right? It doesn't shoot the whole field down, but we have to figure out what's happening here. And so I think it's a call to arms for the people in the quantum computing programming community. And it's especially directed at all the startup companies that are using this algorithm around the world to just blindly apply this to like data that they're getting from some company. It's like, guys, we're like the only ones that ever tried to break this or what, right? So all of the stuff that they're doing when they report the good results is over here. It works with short circuits over here. Remember, 55, 100 variable optimization, that's the length of the circuit. That becomes very difficult. So going further, the performance of QAOA exhibits strong dependence on the density of the problem instance. right? And we call that a reachability deficit. And we should get the second round of reviews back. So we're kind of ongoing work. Now, one of the problems with using quantum computers for machine learning, we'll go through this kind of quick because how many more minutes do we have left? Should be about 20. Okay, good. So good for me, bad for you. This is when it gets really boring. No, just kidding. So, we wanted to jump on the bandwagon and just do something that like showed how amazing it was. So here's the problem with machine learning on a quantum computer. You have classical data, then you have a quantum circuit, then you read it and you read out classical data. So like, what's quantum about that? I don't know. Right? So you're just basically doing classical machine learning with a quantum processor, which maybe that's cool. I mean, the D-Wave, there's machine learning models, which are called generative models, which are, the restricted Boltzmann machine. This is somehow, it's an Ising model, okay? It has a different topology, a different graphical network structure than the D-Wave, but D-Wave is interested in building that, replicating that. That's probably one way where they can make their machine useful, even if it wasn't a quantum computer. So what we wanted to do, and we were inspired by this like kind of onslaught of, let's say, low quality machine learning papers in physics, where all they're doing is they're basically training a neural network to decide what phase of matter it is. They're getting more sophisticated now, but you have to already know the phase of matter. So it's supervised learning. Unsupervised, what they'll do is they'll pretend they don't know and they'll basically run a loop, and then they'll look for like when the curve starts, and then they'll kind of zoom in on that and they'll call it unsupervised. Okay. Now, what we're doing is we're replacing the classical machine learning algorithm with a quantum algorithm. So it's a quantum phase detector, phase of matter. So one of the first things that, so it was more than that. So one of the first things that we'll do, so everybody that was around for a while in tensor networks, there's a thing called an area law. And so what my statement is this: a low depth, hardware efficient ansatz. Does everybody know what that is? So if you have your Hamiltonian of your system, it's coupled together with a natural graph. That's called the connectivity graph. You put your circuit on top of that in time, right? That's the hardware efficient ansatz. The hardware efficient ansatz with a low depth circuit satisfies what I call a combinatorial area law. So in other words, you can bound the number of E bits between any bipartition by looking at, very simple. You chop this, you let this thing evolve a little bit. You split it in half. How many wires did you cut? The wires are the two body gates, right? The number of wires you cut, the minimum over that, the minimum over partition A, which is the number of qubits on side A, the minimum over partition B, that is the maximum number of E bits that your computation could sustain. And so what you do is you go on and you basically assume that you have bipartitions that are exactly in half or approximately in half. And then you assume that you have circuits that saturate that. And we call those like perfect circuits in some sense. We need a better name for them. But the hardware efficient ansatz does exhibit what I would call a combinatorial area law. And the question is this: in the low depth circuits, you can saturate bipartite entanglement. It doesn't mean that you can reach any state in your Hilbert space, but entanglement, bipartite entanglement, is a very coarse graining of your space, right? The states that you can produce cannot be, it's not a very good classification of states. Looking at all possible partitions, right? So your entire entanglement spectrum or whatever, this is a different thing. We're not talking about that. We're just talking about bipartitions. So what we wanted to do was we wanted to basically take something that we know from condensed matter physics, throw it at a couple problems, but put it in a circuit language. And on the left, we have, that's actually a tree. And the tree will actually satisfy an area law in the sense that when you partition it, the number of E bits is quite easily calculated because you're going to cut basically some finite number or maybe even one wire. Okay. Where the thing on the right, which is a checkerboard ansatz, this basically will exhibit volumetric entanglement scaling. And what we'll do is we'll let the thing evolve for a number of steps to make it perfectly balanced. So for example, if I have 5 qubits here, 5 qubits here, I'm going to have to evolve to at least 5 gates deep, right? To make it so you could potentially saturate the entanglement. And before going too far, the first step of the algorithm is we run the variational quantum eigensolver to minimize these Hamiltonians, which I think we use the Heisenberg model and an Ising model with transverse field. Then we throw it into a classifier, and the classifier is very simple. It's a tunable circuit. On the output, we count the number of ones. That's it. That's the output, the number of ones. Okay, so it gives you some kind of approximation to a real number on the output, and the thing works quite well. This actually shows, and we have some finite size effects here. This actually shows that it gets worse with lower rank, okay, which confirms what we were expecting. And at the phase transition, so the model has, in the infinite limit, the model would have a phase transition here. Remember, this is a small system, so you have a finite size effect. And the fact that it's drifting over is, again, it's a finite size effect. But everything matches. The thing works, right? So we're reporting, let's say, a positive result, and everybody liked it because we removed the need to feed in the data. We prepare a quantum state. We label it, then we train on that. So we're not feeding in classical data anymore. We're feeding in the quantum state. So that was kind of the punchline of the study. And finally, to conclude this, so what can we do with this stuff, right? So when I first looked at this, I was like, okay, look, you're minimizing a Hamiltonian. Minimization of a Hamiltonian is obviously quantum universal, right? Because you have all of these different constructions. Well, there's a lot of subtleties in the proof, though, right? There's a lot of subtleties in the construction as well. And it's not actually obvious to show this. So the model, the variational model of quantum computation that I've defined is quantum universal. And you have to do two things. You have to give me an objective function where if I minimize it, the minimization process will produce any state that is epsilon close under the 2 norm to a quantum circuit's output. So in other words, I have a quantum circuit over here producing a state. I need to be able to have a penalty function that will produce a very close state to that. But that's not good enough, because how do you do it? You have to optimize something. This is variational. You have to optimize, right? Well, the solution to the variational problem has to be provided. And the solution is given by the gate sequence, unfortunately. But you remember at the beginning of the talk, so you guys get what I'm saying, right? You have to define a solution to the variational problem by giving me a control sequence that is efficiently describable, that will efficiently prepare that state given the quantum computer. But you remember at the beginning of the talk, we went from gates, and I mentioned how you have optimal control. Here's how I imagine this thing will actually work. You put on a few gates, that's inside your coherence time. Those are gates. You can do it. You measure everything, make sure it all works. Then you compress them like crazy. Then you do that as one block. Then you put on some other gates, compress them like crazy, right? So there's some kind of weird like hope here that I think this thing might actually work, right? Now, proving that it's universal is one thing. That's like a mathematical result. Making something practical is something different. So to prove this, and this is something, I recommend if you're going to read something, okay, so send me an email and I'll give you so the version I have on the archive has no proofs in it, right? I just put this on the archive, then I sent it to the journal. The appendix was like this mad mess. And so the editor was like, go ahead and write this so no one can ever read it. And just put all the proofs in the main body. I know it's against the rules of the paper of the journal, but who cares, right? So he's like, his last words were, "I know you want to." And I was like, "Yes, I do actually. Thank you." So the new version, which will come out after the 11th, will go through this construction. So people that are looking at this, especially from the graduate school side, and you have a lot of time on your hands, this is a good one to read. So there's a lot of different good constructions here. And remember, this is my proof, but there's obviously a lot of other pieces that are coming from, 20 years in the field of quantum computation, right? We're using techniques from little pieces. So a lot of it, it'll be a very, very educational piece for a graduate student, I think. There's a lot going on here, but the important part is there's kind of two main theorems. So firstly, if you find a state that causes this to accept, this I get to choose and I construct this, then I can guarantee that I have high overlap with the output of the circuit that I'm trying to simulate. In the first construction, which we call a telescope, it has no dependence on polymatrices, because polymatrices act on your Hamiltonian to only change its locality. It does not change its cardinality, where cardinality is the number of terms needed in the poly basis to express that Hamiltonian. But in the telescoping construction, it has exponential dependence on a general gate. We nonetheless work this out and keep it there because the telescope will actually become an ingredient in the foolproof. Okay, and also it's quite cool because this can kind of be this thing we can kind of experiment around with on like the IBM Q or something. So that's kind of the first piece. The second piece is we go back to this thing. So remember with adiabatic quantum computation, when we proved that that one was universal by Aronoff and some others, and I used that construction for my work on this as well, the problem was the number of clock bits. So you have these slack bits, it grows linearly in the size of the circuit, which sucks, right? That's terrible, right? But here, that's not the case. It's logarithmic because the locality doesn't matter anymore. That we can deal with. And this is the last slide. So this is probably a terrible experience for about half the people here, but you'll pretend it was fun. And that's okay. I appreciate that. I like it. Now, what's the most important thing? I want this thing to be at the same level as the other models of quantum computation, right? Because this is the model that we have. And yeah, people are like, yeah, you're just one of those jerks that just proves stuff right in front of our faces, right? It's like, we already knew of the model, okay? I didn't invent the model. It's like, I'm just looking at what Google's doing. And I just wrote everything down and I proved it. But it's important because I think that there's a technological component to this. I think if we're going to go after something like factoring, I think this has to be understood. And I think that looking at this through like, if you don't understand something at all, which I really believe is where we're basically at with this variational stuff, we really don't understand it. So what we have to do is, okay, we're going to take some risks. We're going to try some different things. I don't think the approach of just showing that it works on some industrial problem where you can't really compare it to the classical version is the right approach. Okay, so I think trying to break this stuff is kind of where we're going, and looking closer at this. And I'm going to continue my work to establish this as a universal model. So the process of peer review is not just, okay, getting the thing published. Yeah, easy, right? It's going to appear. So, but peer review is showing this to a lot of people, discussing it and developing it over a couple times. There's many different scientists who have proven one thing multiple times as they develop that work. And so although the proof is complete here, I could expect that in a year I'll have a different understanding of this, and I will continue to develop that. And I think I encourage other people to look closely at that one, and also look closely at the, look at what we found with with the QAOA stuff. And I say this in all honesty, like there's enough there where we're not going to be competing. So I encourage everybody to look at it. There's some good. It's an easy thing to sort of jump into. There's only one paper on it, right, so far, but it's one where you can't ignore it. If you do ignore it, you can't ignore it forever, because eventually you have to face the fact that we really don't understand what's going on with that algorithm. And that algorithm is the working horse of Google. Did I say that at your premises in Poland? Luckily, I'm in Poland. And with that happy note, like every academic, I'll cite myself at the end just to remind you. And so, I'm extremely busy. I'm one of those people that just turns everything off and I'm just completely focused on my work. But if you do contact me, I'm quite friendly, so I will get back to you. It'll take some time, but if you send me something and it's interesting, we can always communicate. The slides, everything I do is open source. The slides, the papers, everything. You can always get that if you need it. I think it's already on the internet. So
yes, on one
we are also recording this meeting, so the video,
Don't show Google.
the video will be available after the event.
Don't send it to Google.
No, don't worry, it's over.
All right, so is it pizza time? Can I run it?
I think that we still have 10 minutes, so then we have time for questions. Okay. Okay, but first of all, let's thank our great speaker for a very interesting lecture. Thank you, Jacob. Do you have any questions to Jacob now? I think it was quite advanced, so.
You can get the basics off YouTube, guys.
Yes.
I mean, this is, look, if you want to see, I'm going to show you what I'm working on. So I apologize if this, but like, you have to understand, like, I can't do it another way. You have to see what I'm actually working on. So it's not a tutorial.
Fine.
Yeah,
that's fine. So we at some point we'll get to this point as well. So most of people here are at rather the relatively early stage of learning quantum computing, but I know that there are also researchers who are quite advanced. In fact, I have one question, because you said about this variational model, and that you said that it admits to be universal model. So can we already prove that it's a universal model, mathematically proved?
Mathematically proven. Here's the proof goes like this. There exists an objective function, and there is a quantum state that has a control sequence which is efficiently describable in the size of the number of bits that causes that objective function to accept. When that objective function accepts, it produces a state that is E close to the output of a quantum circuit. So it's universal. So remember, there's different types of universality, right? This is computational universality. Yeah, so that's proven. Now the proofs and everything are not on the current archive version. It was just these were in the appendix. Now the new version is actually much different, and I'm putting that up on the 11th.
Okay. Is the proof publicly available?
Sure.
Is it published? Okay.
Yeah, absolutely.
Great. All right. Any more questions?
I apologize.
Maybe
I'm sorry.
we still have some time, so I can call the pizza and ask when they will arrive. But okay.
And this is a polynomial number of gates, yes, in a sense.
So the number of terms in the Hamiltonian is polynomially bounded in the size of the system. And here's the trick, right? So if I just gave you the function, then you're going to say, oh, but how do you minimize it? Well, this is the cheating part. The circuit that you're trying to simulate defines the control sequence that does minimize it. So that kind of completes the proof, and that's a simple part, but it's important because that's kind of the starting point. So yes, it's efficient in that word.
Okay. Any more questions to Jacob? I have also one more question. Can you maybe tell us a bit more about the research group that you work on in? I mean, the Skolkovo Institute of Science and Technology, the Quantum Laboratory.
So we're 23 people now, and we're trying to hire some more research scientists. So people that are finishing their PhDs, if you want to stay in academics, it's obviously there's so many things happening in startups, right? But that you won't be able to come back, guys, because there's going to be somebody that actually knows what they're doing on the other side that are going to say, no, that wasn't real research. You might think it is now, but there's a huge difference between postdoc-led groups and like people that are still kind of active throughout their careers, right? There's a huge difference. So I'm very, very active, and I can really tell what's happening at those startups. That's not going to give you an academic career. You can't have your cake and eat it too. So people that don't want to go make 100,000 or 150,000 in Google, you can come and do a postdoc in Skoltech. We're looking for people, especially from quantum algorithms background. So,
all right.
Minimization of quantum Hamiltonians is in general a difficult task. I mean, if the Hamiltonian is simple, the minimization is simple. If the Hamiltonian is complicated, contains many variables in an involved way, you can very easily, and we know it from our experience, run into trouble like false minima. This is a problem for all these annealing algorithms as well. I hope the D-Wave engineers, they are aware of that and carefully select their systems or engineer their systems that they don't get stuck, because otherwise they may wait, the age of the universe until it anneals. So does it somehow show up also in your approach? You say that you have the parameters, you have a string of AND gates or a circuit, there is some magic which tells you that you have to change the parameters if in a certain way. But
Yes,
how come that this sounds or seems to be free from this problem?
only because I'm cheating. Here's the thing. It's absolutely not free. So what he said is absolutely correct. So look, I have an objective function I'm trying to minimize. I'm assuming that my system is fully controllable and I can execute a sequence of gates. It happens to be the sequence that I'm trying to make the objective function create. Okay, so I act on an initial state with a sequence of gates. Then I want to simulate that output of that circuit using the minimization process of an objective function. The gate sequence prepares a state which causes the objective function to accept. Therefore, it's universal and I avoid his problem. Now I will say the following. Imagine this, if you will. I take a circuit of L gates. And what I do, instead of realizing it as a sequence of gates, I start to try to tune it, to compress it and compress it and compress it. And we have numerical results where we can compress this a little bit. Then I add L+1 gates. Okay, so we believe we can kind of merge optimal control with this. And even though we still have to do that variational stuff, we might be able to do something. Now, I'm speculating here. I mean, it's not going to work absolutely. I would say that definitely, but maybe. So this is our next question. But we don't expect it to be a free lunch. Hello, Google. I'm sorry, Google.
Any more questions to Jacob? Okay.
Sorry. So you have spent some time criticizing the recent supremacy result of Google.
No, I didn't.
Well, but I didn't really understand why. So maybe could you elaborate on what exactly you think is the weakness of what they did?
Man, this is always the problem. So I say a lot of crazy stuff, so people think I say everything and absolutely nothing. So I appreciate that, but this is one of the age-old things. So I don't think that I didn't criticize them for that. I criticized them for QAOA. But so the quantum supremacy stuff, all it is very simple. They do the hardware efficient ansats by intertwining some gates on a lattice, and then they do that. They pick some assignment of the parameters, and they repeat that experiment thousands of times, which can happen very fast. Then what they do is they put a plot, they put a curve out. Okay, that's basically what it is. Then you have to try to reproduce that on a classical computer. Okay, and that's the method. I believe, so far it looks like it's very solid. I haven't went through the paper in extremely fine detail, but I did look through the paper. I think it looks, as long as everything in there is true, like it looks like they did it. So my question is, what else can you do with that short circuit? That's what my question is. And the criticism towards Google, maybe it's funny. Okay, we're in Google, yay, but they have this QAOA, and the instances that they picked are not representative, in the words of statistics. That's what I'm criticizing.
Do you think that we can already draw any useful conclusions from the results achieved by Google in that case? Or how important it is according to your experience, your knowledge?
So the most useless thing that the Wright brothers ever did was the first flight, but it was the most monumental, but it was technologically useless because they flew like 25, 30 meters. Okay. And then there was decades of work to go, now we're going to do 60 meters. Now we're going to do 150. Now we're going to do 1,000 feet. Okay. And it wasn't until really, it was 1903, right? 1903. Okay, when were the first commercial flights? When was the first airplane used in a war? Okay, World War I, that's already 1914, okay? This is over a decade and a half later. So right now, the Wright brothers have been replaced, not by bicycle makers, but by web browser makers, okay? And they made quantum supremacy, and it's just as monumental as something that is like the first time a human being flies, but it's just as technologically worthless.
Can we be sure that this will lead us to something similar? I mean that we are really at the beginning of quantum supremacy, or we cannot be sure yet?
Well, we can never, and that's the interesting thing. So we don't expect there to be an error-corrected quantum computer anytime soon, but we probably would be too pessimistic to say that nothing is possible. And it goes back to the first question I asked at the beginning. Can you find a quantum system that exists in the real world that you can't predict the properties of? The answer is yes. Okay, even that ice bucket that I talked about at the beginning, you can't predict the outcome. If you could simulate this perfectly on a quantum computer, you might be able to. That's the point. So you should be able to have some type of power even in the absence of error correction. Right now, of course, we want error correction, and even my proof relies on error correction in the sense that I'm assuming everything is perfect, right? And most of the work on quantum algorithms, even that I myself have done, 10 years ago or whatever, it assumes that we have perfectly error-corrected system, right? We assume that all the measurements are done absolutely right. In reality, this is not the case.
All right. Any more questions, Jacob?
Yeah, so food for thought maybe. So taking your previous analogy to the Wright brothers and the uselessness of their first flight, do you think that the first useful purpose of this would be war?
I hope not.
So, well, what is it? What will it be? What do you think?
So that's a very interesting question, right? So in some kind of alternative reality, I'm not just working in Moscow. I'm leading the quantum software development for Russia, right? But it's a humanitarian focus, right? So anything that you have, even this microphone, could be used for good or for bad. Like what I've done with it for the last hour is bad, right? No, but could be much worse. You could hit a baby seal with this sucker, right? Just knock it out, right? So we have to assume that, we're all people and that we have, some kind of aptitude for, not destroying ourselves or each other. So I hope nothing I do anyway. I hope, but I'll tell you this, like right now, I'm pretty convinced that what I'm doing at least has no military applications. Pizza time.
Where's the mic? No, I don't do this one. Right. So, any more questions to Jacob? You'll have opportunity to ask questions soon, but first I will just make an announcement because pizza has just arrived, and we need at least 2 people, strong men preferably, to go downstairs and help in just taking pizza here for the after party. And then, you will still have opportunity to ask questions to Jacob. But now we also need help.
Great.
All right. So anyway, let's thank once again Peter for a great talk. I will also give a few announcements, but maybe let's. Okay. I see that 2 people have already gone for a pizza, so I think that I can continue. Just to let you know, our next meeting will be in 3 weeks from now. So Jacob told you about this quantum error correction, and in fact, Professor Rafał Dąbkowicz-Dąbrzański will give a lecture. Probably it will be this time in Przestrzeń from Facebook. The title will be Quantum Error Correction. Indeed. So we already invite you to join, and we have in plans at least 2 meetings this year, one at the end of November and one just before Christmas. So once again, we have links to our groups and mailing lists, so we invite you to join. And we would like to thank once again to Google and Daftcode for supporting us, and I thank you also for your attention. It's time for the after party.